All right, very good afternoon, everybody. How is everyone doing today? Fantastic. Oh, wonderful. Oh, my goodness. You guys, it's just amazing to see so many people here. Thank you all so much for coming. It's just such a pleasure to see everyone. How are you guys all doing today? Good. Are you guys having a good time here? Fantastic. It's been seeing plenty of people still in Scarlet as well. Did you guys have a good time at Scarlet? Nice. So I think this was originally going to be at 10 a.m. and I have to say I'm quite glad they rescheduled it to the afternoon exactly. I think I had a nice brunch this morning. I think that works out pretty nicely. Did you guys have a good time looking around Belfast as well? Okay, beautiful city, isn't it? And I think Dublin tomorrow is going to be absolutely fantastic. So thank you guys so much for coming along this afternoon, where we're going to be focusing about not just one of the biggest questions in science, but arguably one of the biggest questions for humanity. We're going to be thinking about the question of life in space. Now, if you haven't come along to one of these talks before, you are especially welcome, and I am super pleased to see you here. My name is Ed Macaulay. When I am not lecturing on a ship, which I absolutely love, you can usually find me at Queen Mary University of London, where I'm a lecturer in physics and data science. My research background is in cosmology, so studying the astrophysics of the universe at some of the largest scales. And I love trying to make science and physics more accessible. I think it really is something quite important. As we're going along, please do feel free to ask if you have any questions as we're going along. You're very welcome if you want to take any photos, make any recordings. As we're going along, take any notes. On the subject of taking notes, I'd like to include my obligatory reminder that please don't worry, nothing here is going to be examinable. So please do just kind of relax and enjoy the afternoon as we're thinking about this big question of life in space. Now, a bit of a spoiler warning for you guys. We haven't found any life yet, okay? But I think we are really close. And I am really excited to share with you guys some of the places in our own solar system and beyond where I think there really could be very good chances that we might find some of the very first signs of life. And I think this really could come quite soon. And I think this really could be one of the biggest discoveries that humanity could make, and it really would change our perspective of how we fit into the cosmos. Before we get on to some of the exciting and extraordinary places in our cosmos where we might be able to find life beyond Earth, I'd like to start by sharing with you guys one of my favorite stories of making discoveries in astronomy that might serve as a bit of a cautionary tale when we're thinking about the possibilities for finding life outside of Earth. So before I was based in London, I actually spent a couple of years as a researcher in Australia. Now, when I was in Australia, I was doing visible astronomy, so with the same kind of light you see with your eyes. But a lot of my colleagues worked in radio astronomy at the Parkes Radio Telescope in Australia, otherwise known as the Dish for obvious reasons. Just as a very quick aside, I know this isn't the science and movies session, but have any of you guys seen the movie The Dish? Has anybody seen this? Oh, did you guys like it? You like, yeah, okay. So there's an absolutely charming movie about The Dish, about this telescope's role in the Apollo 11 moon landing. It is an absolutely charming movie, and I guarantee that you will love it. So if you do want to see a bit more about The Dish in action, do check that out. I just couldn't resist including that. Now, when I was a researcher in Australia, there was a bit of a mystery going on at The Dish. This was kind of back in sort of 2014, 2015. And for quite a few years, they'd been detecting very strange signals at The Dish, which they called Perytons, because there were these kind of strange things which kind of, these fleeting pulses of radio energy, which they kind of detected as flashes, and then they went away. And they'd been finding them very sporadically for kind of 14, 15 years, something like this. Now, the researchers at the telescope, they knew, because of the directions where they were finding these signals, that they must have been coming from very nearby, so maybe terrestrial sources or maybe something from the sun, something like that. But of course, whenever you get anything like any kind of mysterious signals being detected at radio telescopes, there's plenty of news saying, oh, radio astronomers are baffled and maybe is it aliens and all this kind of stuff, okay? Now, it's a bit of an informal slogan at every astrophysics department the world over that it's almost never aliens. It's almost certainly not aliens, because there have been time after time when there's been a slightly mysterious thing, a slightly strange discovery, and people said, oh, is it aliens? And it turned out not to be aliens. So if you remember, it's almost certainly not aliens. And of course, that was what happens here, because one of the researchers who was working at the telescope, Emily Petrov, who was a PhD student at the time, she was studying these signals, and she led the research that actually figured out what was going on here. Because you've got these very short, intense pulses of energy. Now, in astrophysics, that's actually really unusual to have something that just lasts a few milliseconds, because on astrophysical scales, that's such a short period of time, and even a big explosion, you'd expect that to take a lot longer. So it was a real mystery what these signals might be. And then Emily, she noticed when she's going through this data that a lot of these bursts, they tend to happen round about lunchtime. And this is kind of quite sort of surprising, a little bit curious, because if you were getting, bursts of energy from the sun or maybe something from the atmosphere or lightning, you wouldn't expect it to be happening always around lunchtime. That's quite a curious time for these things to happen. And then when they probed a little further, they realized that the frequency of these radio waves they were getting was the exact frequency of light, frequency of radio waves, that you get from microwave ovens. So then they're starting to think, okay, what might be going on here? Okay, so they test some ovens and they put some stuff on, they don't get any signals. It turns out where you get these signals are if you're making your lunch in a hurry and you just jam the door open while it's still running. So the microwave does turn itself off, but in those few milliseconds between you opening the door and the power going out, it's still emitting radio waves for just a few milliseconds. And that's what they've been picking up at this for years and years and years. And people have been writing papers about it. The news is saying, is it aliens? So if you're wondering, is it aliens? Maybe it might be aliens. Or maybe it might just be someone microwaving their lunch in a hurry. So it's important to bear that in mind. Now, I'm sure you didn't come here expecting also to get a bit of day-to-day practical cookery advice as well. But I think also I might suggest that next time you're microwaving your own lunch, I would suggest make sure, do just turn off the microwave, making sure it stops, and then open the door. Okay, don't just jam the door open, because you just get a few milliseconds of the microwave running. So just turn it off, then open the door. Okay, don't be a hero, and then you can enjoy your lunch. So I think this serves as a bit of a cautionary tale. Whenever we see anything which we start to think, okay, maybe that might be life, that it's important not to jump to conclusions. And it's important to think about, okay, are there other ways, are there kind of geological ways, non-organic ways that we might be able to get signals which look like life? Something which has changed, though, really over maybe even the course of just my career, is that once upon a time, the search for extraterrestrial life was really kind of on the fringes of research. And it kind of wasn't the sort of thing that you would have going on, like in a respectable university astrophysics department. But that really has changed dramatically. And now the search for extrasolar planets, exoplanets, and life in other places in our own solar system and beyond, it's now a very serious field of research, and there's journals and serious publications about it. So it's gone on this amazing transformation. And part of the reason is that the researchers who specialize in this are really starting to pin down the essential ingredients that you need if you are looking for life beyond Earth. Now, my academic background is very much in physics, so I kind of approach this very much from a kind of physics sort of angle. But maybe if you've got a bit more experience with biology, then that's a kind of different way to approach it. But I think it's quite useful to take a bit of an overview of what some of these key ingredients might be for life, and also where we see them in action in Earth. So I have this really beautiful picture of the Grand Prismatic Spring in the Yosemite National Park. Has anybody seen this? See, I would love to visit. What did you guys think? Did you see all the beautiful colors, all this kind of stuff? Now, one of the reasons why this is interesting in the field of exobiology is because this is one example where we find very extreme life. So even in these very hot springs, where it's kind of far too hot, you wouldn't expect life to exist there, we still find microbial life which can survive there. And I think this image here is a really good example of the three kind of key essential ingredients which we think you're going to need wherever you're looking in the universe if you're looking for places where you might find life. Now, the first ingredient, this really very much plays into my kind of sensibilities as a physicist, because when we're looking out for life in the universe, I'm sure it could be all kinds of surprises. And the reality is we have no idea what life elsewhere in the universe might look like, what it might be composed of. But I think the one thing which we really can be pretty sure which any form of life in the universe is going to need is it's going to need some form of energy. This is kind of like the single most important thing that we need in order to have life in action. Now, so much of the life on Earth, that source of energy is the sun, so plants from photosynthesis or other things which then eat the plants and all the way up the food chain. But in these hot springs or deep under oceans, that source of energy is from thermal vents, thermal springs. So it's still providing that source of heat, that source of energy that you need for life. So wherever we're looking for life elsewhere in the universe, I think one of these key things is there's got to be some source of energy. Maybe it's the star, maybe there's some other sources of heat, but that's kind of the first key ingredient. The second essential ingredient, which seems to be a kind of unanimous essential feature for life, it's also still kind of, I'd like to think of this as kind of within the realms of physics here, is that it really seems important to have a liquid, some kind of liquid medium for the life to exist in. And if you kind of think about this just from a physics point of view, if you think about a solid, it's kind of difficult to imagine life evolving in a solid. Everything's kind of too stationary, there's not enough motion, you just can't get enough dynamics for life to evolve. On the other hand, if you think about a gas, everything's just floating around all over the place. Again, it's kind of difficult to think that you just get enough time, enough kind of structure, enough complexity for life to evolve that's purely based on gases. Whereas liquids, they're kind of in this Goldilocks zone. They're kind of not too rigid, but not too fluid. They're kind of just right to give those kind of conditions that you've got enough dynamic stuff for life to have a chance to get started there. On Earth, of course, the liquid that we all rely on is, of course, our favorite H2O. So a lot of the search for life elsewhere in space is the search for liquid water, because almost everywhere on Earth where we find liquid water and some energy, we find that there's evidence of life. So it's a good kind of natural starting place if we're thinking about where else we might find life elsewhere in the universe. Now, water might not just be the only game in town. There's some possibilities. Maybe we could have methane-based life. That's going to be a lot colder, but potentially that could be a liquid, or maybe even a bit more exotic ammonia-based life. But water's got quite a lot going for it. It kind of bonds very nicely. You can do kind of a lot of chemistry quite nicely. And also from a cosmology point of view, the ingredients for water, hydrogen and oxygen, are relatively abundant in the universe. So there's kind of good kind of natural reasons to think that looking for water is a pretty good first step if we're looking for life. Now, the third essential ingredient that we think we're going to need for life is also very much in this image, And it's where we kind of start going from physics to a bit more the kind of chemistry and biology side of things. And it's that we need some kind of chemicals, some kind of organic molecules, maybe a little bit of carbon, a bit of nitrogen, this kind of stuff, in order for life to have something to work with here. The way I like to think about it is a bit like if you think you've got like a set of Lego bricks, right? You can make the Lego bricks into anything you like, but you've got to have some bricks there to work with, right? If you don't have any Lego bricks, you kind of can't make anything. So even if you do have a good source of energy, maybe the sun, and you have plenty of liquid water, if there's no molecules there, no carbon, maybe a little bit of iron might help, then it's kind of difficult to imagine how that's going to evolve into life and not just be completely sterile. Okay? So these are the kind of three ingredients which we think we're going to be able to look for when we're looking out into the solar system and beyond for traces of life. And we find them in the kind of extreme environments in Earth, and everywhere on Earth where we find life, we find these three key ingredients. So they're a pretty good starting point. And that's going to be a bit of a theme as we're looking out into the cosmos for places where we might be finding life. So for our first kind of step away from planet Earth, I'd like to take you guys to a dwarf planet in our own asteroid belt, where there's been some very recent breakthroughs that suggest they might have found all of these three kind of key ingredients. So, a source of energy, maybe the possibility for liquid, and also some molecules. And it's this dwarf planet here, Ceres. So it's in the asteroid belt. And I know it looks pretty cool and pretty kind of sci-fi here, but this is not CGI or anything. This is just an enhanced color mission from NASA, enhanced color image from NASA's Dawn mission. And what you're seeing here, it might look like ice, but it's not actually an ice cap. It's actually salt residues left over on the surface. And that's really interesting. How do you get a big old kind of crater full of salt? And what this suggests is maybe in the past, so maybe a couple of billion years in the past, maybe there used to be kind of liquid water, which then kind of evaporated off and left this, this kind of salty residue in the crater. Now, Ceres doesn't look at all habitable today, but there's kind of evidence from this mission that maybe kind of a couple of billion years ago, it might have been more habitable because it had all these three ingredients. Now, the energy source for Ceres actually looks like it might have been coming from within the rocky world itself. So it looks like there could have been heating in the core, and that thermal heat from the center of the planet, that's what's giving you the heat and the energy you need to get liquids flowing. So it's not relying on heat from the sun. But of course, as the world cools down, then eventually it's kind of going to run out of that energy there. So it looks like from those salty deposits on the surface that there might be reservoirs of salty water contained within Ceres. So potentially, maybe there might even still be kind of evidence of liquid that was once there. And then also there's traces of elements, of molecules, maybe things like carbon dioxide and methane, which, on Earth they're potentially signatures of life. We're all exhaling carbon dioxide when we're breathing, and then methane also another trace of life. And all of these things have been found just on Ceres. So the energy, the warmth, the liquid, and some molecules. What this means is that maybe a couple of billion years ago, when Ceres was a bit warmer, it might have been potentially habitable. And this is just one rocky world within our own solar system. And this doesn't even rely on our own sun as a source of energy. Of course, on Earth, the sun is really the kind of powerhouse which gives us all our energy. In a sense, we're kind of indirectly solar powered, right? Because the plants, they start with the photosynthesis, and that's how the energy gets into the food chain. So the sun is really important for thinking about where we might find life as a source of energy, but also to give us the necessary heat we need to give us that second essential ingredient for life, and that's some form of liquid. So we've got this diagram here from the European Space Agency, and what this illustrates is what's called the habitable zone around our own star, the sun. And the idea is that if you're too close to the sun, like Mercury or Venus, it's too hot, okay? It's too hot to have liquid water, it's too hot to have life. Whereas if you're too far out, so Mars just kind of right on the edge, but by the time you get to kind of Saturn and Jupiter, you're too far out. It's too cold to have liquid water sustained by the sun. But in this region in between, where Earth is and then Mars just on the edges there, that's the Goldilocks zone. It's not too hot, it's not too cold. It's the habitable zone. So it's where there's going to be enough energy to give us liquid water, but it's not going to be too hot or it's not going to be too cold. Now, in our own solar system, this gives us an idea of where we might once have been able to find life elsewhere in our own solar system. But also, if we're thinking about life beyond our solar system, this is actually a very useful model to think about where we might be finding habitable exoplanets. Because, if they're too far away, they're going to be too cold. If they're too close in, they're going to be too hot. The first planet that I'd like to take you guys to next in the habitable zone, it is the planet Mars, right on the edge of the habitable zone. Now, the first lecture we did here was all about space tourism and the prospects for visiting space. Now, of course, at the moment, we only have robotic missions going to Mars. But did anybody, I know Scarlet Night was all very exciting, did anybody see the news about the SpaceX launch, which happened just overnight? Yeah, so incredible news. So SpaceX did the kind of first fully successful test flight of their really huge new Starship rocket. So this was the first time they'd launched this rocket, and they'd recovered the booster, and they'd safely recovered the Starship, the thing which goes into orbit. So this really is a huge milestone in the potential for space exploration. And I think just literally overnight, it really has made the prospects for humans visiting Mars, a whole lot more realistic. And maybe about a couple of years ago, the Jet Propulsion Lab in California, they put out an absolutely charming series of kind of hypothetical travel posters, kind of just illustrating, what traveling to, Mars might look like. So this is the one they did for Mars. I just really love the design that they put in there, and just kind of highlights the idea, that, maybe one day this might actually be a genuine destination. So I love that, they had a bit of fun, took a little bit of artistic license with this. And they've made some really beautiful posters for various other destinations that we might be thinking about. So I love the design of them, and I think it kind of just serves as a little bit of a kind of an outline for some of the planets that we might be thinking about this afternoon. So first stop on the tour is, of course, the planet Mars. Has anybody seen Mars through a telescope? Okay, wow. Quite a few of you. Did anybody see, you can actually see this if you have some good viewing conditions. Did anybody see the polar ice caps on the top of Mars? Okay, fantastic. Do you know what kind of telescope you were observing with? Yeah?
No, it was a telescope.
Okay, fantastic. The thing is, you don't even need a huge telescope to see the polar ice caps there. So this image is from the Viking orbiter. So we've known for a long time that there's water ice in the polar regions of Mars. Now this is really exciting if we're thinking about visiting Mars, because it means you don't need to bring all the water with you. There's already the ice there if you can only melt it. But for a lot of time, when the researchers were first studying Mars, it really seemed like a very kind of barren, very sterile, cold planet. But as we're starting to kind of look more closely, it looks more and more like there could be evidence that Mars at least once was habitable, and just maybe there's a chance there might still be a microbial life on Mars. Now this is our current best robotic Martian explorer, so the Perseverance rover. So this is a brilliant six-wheeled rover developed by the Jet Propulsion Lab, JPL, and it's looking for kind of evidence of past habitability on Mars. So NASA have had an extraordinary series of robotic missions to Mars, to the surface. And they really found that it looks like Mars used to have an abundance of liquid water on the surface. So it looks like there used to be lake beds and rivers. So there used to be an abundance of liquid water flowing on the surface of Mars. Don't you guys think that's just absolutely incredible? So maybe a couple of billion years ago, there could have been like water that you could have drunk just on the surface of Mars. It looks like, though, so maybe a few billion years ago, Mars was warm enough to be habitable and have liquid water. But once Mars cooled down too much, its magnetic field stopped, and then the whole kind of house of cards fell apart, because once its magnetic field stopped, it had no protection from the kind of solar winds and solar radiation, and that blasted off its atmosphere, and now it's a very kind of cold, icy, rocky planet, much more sterile than it used to be. But the evidence looks like it's increasingly building that Mars certainly used to be habitable, and there may even be kind of still traces of liquid water on the surface, and there's a kind of real possibility that there just might be microbial life still existing on Mars. One of the best places that we might be able to find microbial life on Mars is it might actually be preserved in the remnants of impact craters on the surface of Mars. This is a false color image from the Mars Reconnaissance Orbiter. And this stuff which has been colorized here, it's called impact glass. It's actually glass which is formed when asteroids impact the surface, and that real heat turns all the kind of silicates and things into glass. And what's interesting about this is it might be somewhere that could have preserved the ancient kind of organic molecules and maybe any of the ancient evidence for life. So what they're finding with Mars Reconnaissance Orbiter is, okay, maybe this might be a good place to go and send future missions to look for more direct evidence of life. The last exciting thing I'd like to share with you guys about the prospects for life on Mars. So this is methane detected in the Martian atmosphere in spring, summer, autumn, and winter on Mars. And you can see that there's a seasonal variation in how much methane is concentrated in the atmosphere. Now, there's other ways that you can get methane, other than just from life, so, from kind of geological processes. And there are other ways you can get seasonal variations with methane in the atmosphere. So maybe when it's warmer, maybe some of the ice melts, and that's releasing some trapped methane. There's other geological mechanisms. But just maybe, there might be some kind of biological processes which are also involved in this. So my take is that all the signs on Mars, even though initially it looks like it's a very cold, sterile, barren planet, once you just start looking a little bit close, there's evidence for plenty of past liquid water, all of those ingredients that we think are essential for life, you can find them all on Mars. And there's very tantalizing hints that there might be kind of still microbial life on Mars. So it really is a very, very exciting destination for future exploration. And I would love to come back in a few years' time and see, just maybe there really might be signs of life to be found on Mars. Now, Mars is at the edge of the kind of conventional habitable zone in our solar system. It's right at the edge of that Goldilocks zone. If it was just a bit further out, it never would have been warm enough to be thinking about liquid water from the sun. But there's actually other places in our own solar system outside the habitable zone that also have all of these three key ingredients for life. So energy, some liquids, and some kind of potentially organic chemistry. And the first place we might look for this are in the moons of Saturn. Now, this is an absolutely beautiful image of Saturn taken by the Cassini spacecraft. Now, I can tell you as a point of fact, actually, I can guarantee you, there is one habitable world in this photograph. Can you guys see this tiny little point over here? Can you guys notice this? Earth, absolutely, that's Earth. So I can guarantee you, there is at least some life in this photo. And I think it really does put our whole planet into a little perspective there. I think also there is also Mars and Venus up there as well. But Saturn, even though it's outside the habitable zone of Earth, it looks like there's a couple of moons where there might still be the potential conditions for life to exist. And the first one is the moon Titan. Now, Titan is a very, very cold moon, and it's far too cold to have liquid water, but there's an abundance of methane on Titan. So there is a possibility that it might be able to support methane-based life, and in principle that could work. You know, it's going to be a liquid, it's going to be very cold, it's going to be a lot slower, but in principle, we've got all those pieces of the puzzle that we need. This is a photograph of the surface of Titan taken by the Cassini mission. And from the surface, it just looks like this kind of hazy ball of just these kind of clouds of methane, so you can't really see too much from the surface. But this mission, Cassini, it released a lander, the Huygens lander, and actually made it all the way to the surface of Titan, which is just like so exciting. I mean, my research background is cosmology. We're looking at things, you know, billions and billions of light years away, and you can just about see a few pixels through a telescope. So the idea of studying something where you can actually put something on the surface, like, to me, it is just like unbelievably exciting. And there's footage from the Huygens lander of its descent all the way down into the surface of Titan. And it looks like, you know, there's evidence of, you know, this kind of flowing liquid methane. So, you know, we've got, even though it's kind of too cold for water to flow, we still do have that kind of liquid. So just maybe there might be the chance for methane-based life. Now, Huygens was the first probe that made it down to the surface, and it was really kind of a real pioneer in that respect, but it didn't have the capability to kind of look too much further for any additional signs of life. But NASA is planning another mission to explore the surface of Titan. It's called the Dragonfly mission here. So this is a computer rendering of it. Now, this is a nuclear-powered octocopter. How cool is that? You don't get to say nuclear-powered octocopter very often. So it's a bit like those kind of drones, those kind of quadcopters that you have, but it's got 4 propellers, so it's an octocopter. And this thing at the back, so Saturn, it's generally, you know, kind of too far away for solar panels to be very effective. And then, of course, Titan, you're underneath all that hazy atmosphere, so it's got a nuclear generator, kind of quite similar to the ones in the most recent NASA Mars rovers. And this is really being designed to look specifically for, you know, the possibilities of life on the surface of Titan. So, you know, right now, this mission is being, worked on. The plan is to kind of launch in the next few years and maybe reach Titan, you know, in the kind of 2030s. And this really could be, you know, one of the missions which makes a big breakthrough in the search for, you know, life elsewhere in our solar system and the, you know, prospects for habitability. So it's just one of the kind of really very exciting things which I'm kind of looking out for over the next few years. Titan isn't even the only moon in our solar system which could potentially be habitable and could potentially have life. So the next place I'd like to take you to is Enceladus, so another moon of Saturn. Now, Enceladus and all the moons of Saturn, they're outside our habitable zone, so you might think there's no chance of getting liquid water. And from the surface, it just looks like this big, icy kind of planet. I'm a big Star Wars fan, kind of reminds me a bit of Hoth from the surface there. So from the surface, it doesn't look like there's kind of much prospects for liquid water. And it's certainly not receiving enough warmth from the sun. But something very interesting happens if you're a moon kind of very nearby to a planet, or even a planet very close to the star. Because, of course, you know, we're all familiar with the tides on Earth. So the gravity of the moon is pulling the water of the Earth. So whenever you have 2 moons or 2 planets close by together, you get these tides from the gravitational forces, just because the nearest side of the planet or the moon, that gravity is that much stronger than the furthest side. And that's, you know, in the case of Earth, it's pulling the oceans and it's giving us the tides. And pulling all this matter around, that actually generates friction. So you, essentially, Cassini is being kind of squished and squashed by the gravity of Saturn as it's orbiting it. And this squishing and squashing it's almost, you can think about it like the moon's getting kneaded by the gravity of Saturn. That gives it just enough heat, just enough energy to keep some of this ice as liquid water. So I think it's amazing how kind of nature finds these ways to get potentially habitable zones, outside of the conventional Goldilocks zone of our solar system. So we think there could be, liquid water underneath, and one of the reasons is that we've actually observed these plumes of water vapor breaking through the icy crust. So it really is very exciting, and we can kind of observe these, and there's some evidence that there could even be kind of organic molecules inside there. So this is measurements from the Cassini mission of some of the constituents of what it's found in these plumes which are being shot out from that icy rocky surface. So there's methane, there's water vapor, also simple kind of organic molecules, and then the more kind of complicated stuff. So we've got pretty direct evidence that there are all of these three essential ingredients that we need for life, and there really could be a chance that underneath this icy surface there's going to be kind of oceans of water, and they really could be containing life. So it really is such an exciting destination when we're thinking about habitability, and potentially there could be microbial life, bacteria, that kind of stuff. Just maybe there might even be macroscopic life. It's not totally crazy to speculate that this just might be somewhere where we might even find macroscopic life. The last place I'd like to take you within our solar system is one of the moons of Jupiter, so Europa. Now again, this is outside the conventional Goldilocks zone of our solar system. It's too far away to be kept warm by the sun. But again, that kind of gravitational tidal forces from the huge gravity of Jupiter is enough to keep some of the water liquid in the same way as Enceladus. So again, from the surface, it kind of doesn't look very promising, looks a kind of pretty barren, rocky world. But again, this is somewhere else where potentially underneath we might find very expansive oceans of liquid water with potentially the kind of other organic ingredients that we need for life. I think it really would be fair to say that when it comes to the search for life on these kind of moons of Jupiter and Saturn, we really have literally not even begun to scratch the surface. But something why I'm so excited about Europa is just last year, NASA actually launched a mission specifically to orbit Europa and look in more detail for signs of life and potential habitability. So it's on its way to Europa right now, and in the next few years it's going to be entering the orbit and really studying this moon in a lot more detail, and maybe trying to identify the places that are going to be most suitable for life and the best destination to follow up, with maybe a lander or something which might be able to explore under the ice and search for, more directly for signs of life. So in the past few years, our solar system has gone from being somewhere where we didn't think there was any prospects for life at all, to actually, there's kind of half a dozen places that have all of these three key ingredients. So some energy, some liquid, some kind of organic molecules where we might be able to get some chemistry for life going. And I really think that there really just might be a chance that we might be around to see some convincing detections of life elsewhere in our own solar system. So I think that really is such an exciting prospect. Now, we're kind of getting to the edges of where we might find habitable worlds in our own solar system. But something that's been such an exciting development in the past few years of astronomy is the ability to find planets outside our own solar system, so exoplanets. And the search is really now on in earnest to find habitable exoplanets and signs of life. And one planet that I'd really like to share with you guys is called a TRAPPIST-1e. So this is one of the planets within an exoplanet system called TRAPPIST. Now, this was first discovered by a small telescope on the ground and then kind of confirmed with a space telescope. And it's only about 40 light years away from Earth. And I can tell you, in cosmological terms, that is basically just next door. Okay, 40 light years is just kind of no distance at all. So it would still be, 80-year round trip just to say hi, just to send a message. But in cosmological terms, this is really, really nearby. Let's take a look at the how this system was discovered, because these planets are, unbelievably small compared to their stars. But my colleagues who work on exoplanets have developed all kinds of very smart techniques to detect the kind of signals of planets orbiting other stars. And one method which has been very promising is called the transit method. So if we imagine a star here and a planet orbiting it, if it's just orbiting it, we can't really see much evidence that the planet is there. But if we're lucky and the planet goes in front of the star, if we see the light that we get from the star, we notice that it dips while the planet's going in front, and then it kind of pops back up. And this is called the transit method. And it's been very, very successful as a way of finding planets around other stars. So you monitor stars and you look for this kind of sudden dip, and then you look for the brightness to return. And that could be a signal that you found a transiting exoplanet. Another advantage about this method is as the planet's just going in front of the star, the light from the star is shining through the atmosphere of that planet. So if we look at the spectra of light that we get, you can actually get some details about the atmosphere of the planet. So not just get confirmed that there's a planet there, but you can also get some ideas of what the atmosphere is like, what kind of gases, maybe even what kind of molecules are in the planet. Let's take a look at this TRAPPIST system in more detail. So for a bit of context down here, this is the inner planets of our solar system, Mercury, Venus, Earth, and Mars. So to scale, the TRAPPIST system is very, very small, a much smaller solar system than our own, because the central star, it's a very small red dwarf star. So to scale, there's the red dwarf star, and then our sun is a lot bigger. So it's a very small star, and all of the planets are much closer into it. Now, normally, if it was a sun like a star like our sun, that would be far too close to be habitable. But because the star is this very small red dwarf, and it's much cooler than our own sun, planets can be habitable if they are much closer. And it looks like maybe these planets in the middle of the TRAPPIST system, maybe especially this TRAPPIST-E here, really could be very good, potentially habitable places in this system. So they're in this Goldilocks zone, not too hot, not too cold, kind of good terrestrial worlds. So, if there's compelling evidence for liquid and the other ingredients we need for life, these really might be some of the places where we might find some of the first signs of life. One of the amazing things about this kind of transit method of finding exoplanets is just how many planets is being discovered. When I first began my career, it was a real mystery, how many stars have planets, and maybe a few stars were detected with these very big they're called like hot Jupiters, very close nearby, but not at all habitable, and only a handful of them are found. But it now looks like almost every star has a planetary system, and a good fraction of them might be habitable. So potentially there could be thousands and thousands of habitable worlds in our solar system. Now, very recently, did you guys hear about this in the news? There was this amazing discovery by JWST looking at this system called K2-18b. It sounds a bit like a droid from Star Wars, but it's actually a planet in this system. So this is an artist's representation. Okay, this is not a photograph. So this exoplanet, it's also orbiting a red dwarf star. So a very small star, a lot cooler, and it's orbiting a lot closer. And it orbits about a lot faster, so even faster than like once a month. And that actually makes these things easier to detect. And this exoplanet made the news this year because for quite a few years, exobiologists, exoplanet astronomers have known that there's water vapor in the atmosphere of this planet. So, maybe it could be habitable. And just this year, there were the first hints of evidence that just maybe there might be signatures of chemicals which are coming from life in the atmosphere of this planet. Now, this is a spectrum of light of the atmosphere of this planet. So this is a wavelength here, so shorter wavelengths going to longer wavelengths. And this was the spectrum measured by the JWST by looking at the atmosphere of this planet when it's transiting in front of the star. So we can see here there's definitely methane, there's definitely CO2, but the thing that really made the news was that just maybe there's hints of what's called dimethyl sulfide. Now, this is where we're really kind of getting outside my wheelhouse as a kind of cosmologist and a physicist and getting squarely into the kind of biology. And in a way, that's what makes it so exciting and so interesting, because dimethyl sulfide, one of the main ways we see it on Earth almost exclusively, it's produced biologically. There are some ways that this might be produced from kind of geological processes or not biologically. But on Earth, it's almost definitely biological. Now, there's kind of two big questions hanging over this. So for one, it's not a totally compelling detection that it is there in the atmosphere of the planet at all. So maybe it might be one of those things where you kind of see a bit of a hint, but then you look a bit more and it kind of goes away. That's the first question. The second question is, if it is genuinely there, is it due to biology, or is it due to some process which isn't biology, which is producing the dimethyl sulfide? So these are two big questions hanging over it, but these are questions which we could probably answer with further observations. So in the next few years, if we get some more observations with JWST on this, this might really be able to confirm if this DMS is in the atmosphere, and then if we kind of study it some more, just maybe this might be what the first signs of life being detected outside Earth might look like. And I think in a way that's probably one of the kind of the best ways to take this, just what might it look like if we do detect life elsewhere in space? Just what might the very first detections look like? It might look like a convincing detection of dimethyl sulfide in the atmosphere of an exoplanet that we say, okay, this can't be due to geological processes. That's what our first hints of life in space might look like. Thus far, we've really only been considering the essential fundamental building blocks for biology, energy, liquids, basic chemistry. And we've really tacitly been thinking about, can we find microbial life, the hints of the most kind of basic life. Before we wrap things up for this afternoon, I'd just like to spend a couple of minutes thinking about a little bit more ambitiously about the search for not just life, but intelligent life in space. Because again, this is something which has gone from being a very much kind of fringe, niche kind of field of research and study, to now it's something which, in the kind of academic astrophysics community, starting to be taken a bit more seriously. This image here is, one of the arms of our Milky Way, so all these beautiful stars in here. So there's thousands and thousands of stars out there, and we now know that almost all of them contain planets, and a good fraction of them could be habitable. So I think it's not unreasonable to start to ask the question, do any of these contain intelligent life? And really one of the pioneers of this was Drake in the 60s. He wrote down the Drake equation. How many of you guys have heard of the Drake equation? Okay. Now, I know nobody comes on vacation to take math class, okay? And certainly, when I was in school, it was by far my least favorite subject. But I just would like to share with you guys just this one equation, because I think it really does kind of map out how we might approach to begin to ask the question, is there intelligent life out there? So if you're really not a math person at all, you can kind of take this as a bit of just a sketch of an outline for what the search for intelligent life might look like. Now, I'll give you guys just a quick safety warning. It's quite a big old equation. Okay? It's going to take up most of the screen here. Okay? But don't nobody panic, okay? Because it's just multiplying numbers together. Okay? So there's going to be 7 numbers there, and we're only multiplying them together. Now, when I was at school, I was not a fan of division, but multiplication, that was okay. Okay, so we're going to see an equation, It's going to be quite big, but remember, we're just going to be multiplying some numbers together, okay? So don't nobody panic, okay? Let's take a look at the equation. Let's see what it looks like, okay? So I did warn you guys, it's quite a long equation here. But what this equation is, it's a way that we might be able to estimate just maybe how many other planets out there we might be able to communicate. That's what this big number n is, the number of planets, the total number of civilizations that we might be able to reasonably communicate with. And you can kind of begin to sketch out how you might calculate this. So the first thing this depends on is really how many stars are out there in the Milky Way, and really how often is the Milky Way forming stars. Okay, so our star formation rate. So you've got to have stars to begin with. The next piece of the puzzle is what fraction of these stars have planets? Because it's no good just having a star without any planets. You might be able to guess what's coming next. Which one of these planets could in principle support life? This doesn't mean they definitely have life, but just maybe they could be habitable. So then amongst those habitable planets, how many of these do go on to develop life? So then you've got life, but maybe it's just microbial life or plant life. We're not going to be able to communicate with it. So the next thing is which fraction of these go on to develop intelligent life? And then of that intelligent life, how many could we communicate with? Then the last piece of the puzzle is L. This is how long is that civilization going to exist for? Because if you develop the ability to communicate with us, but your civilization is only around for a few months, that's not going to work out so well. Now, when this equation was first written down, we really had no idea what any of the numbers were, and certainly no idea what this big old n is. But it was a useful way to start thinking about how we might go about finding life elsewhere in the universe, and also to kind of codify, what do we know, and where do we need to go and find out some more. Okay? And something which has really changed over the course of my career is that a lot of these numbers have gone from being total unknowns to being something that we actually know a little bit about here. So this first number here, the star formation rate, this is actually reasonably well known. Okay? We can count how many stars the Milky Way is forming each year. It's forming, maybe 1, 2, 3 stars a year. Okay? So there's a total of about 100 billion stars in the Milky Way. So you could give everyone on the planet Earth a dozen or so. Okay? The whole galaxy, it's forming about 1 to 3 stars per year. Okay? That's something which has actually been known reasonably well for a while here. What has changed in the past few years is how well we know these two numbers here. Okay? So we now know, if you remember, that almost all stars that we can observe have planets. Isn't that absolutely incredible? Isn't that extraordinary? When I began studying physics, we didn't know this. This was just a big mystery. Now, it might not be 100%, maybe it's going to be 70%, but almost all the stars out there have planets. How many of these planets could be habitable? Just based on what we've seen from transits and the Kepler mission, it could be as many as 10% of these are habitable. Isn't that extraordinary? Next time you look at the stars at night, just think most all of them have got planets, and maybe 1 in 10 of them could be habitable. Next time you're out looking at a starry night sky, you're almost certainly looking at stars that contain potentially habitable worlds. Now, what fraction of these go on to develop life? We have no idea whatsoever, okay? We know life is developed on Earth, but we have no idea what fraction of these habitable planets is going to go and develop life. We've got half a dozen potentially habitable worlds in our own solar system. There's life on one of them, but we really have no idea. Once you have life, what fraction develops intelligent life? We have even less of an idea, okay? Even less of an idea. And of course, what could be communicated? Even less cubed, okay? How long is it going to last? We have no idea whatsoever, okay? As a civilization, we've been sending out radio waves for... Is this first contact here? Is this aliens? This is the moment. They really picked their time in here. Are we just getting feedback here? With thumbs up? Okay. Don't worry, guys. It's not aliens. That's a relief. It's microwaves.
Yes.
Somebody's making their lunch. Talk about timing, eh? So yeah, radio waves. You've got to watch out for them radio waves. They can really trip you up. As a civilization, we've been sending out radio waves for 100 years. Are we going to still be sending out radio waves in another 100 years? We'll have to find out. So for the time being, we have some idea of what these numbers are. These are a total mystery. The last kind of bit of science I'd like to share with you, guys, though, is that this search really is now kind of going ahead in earnest. So these are radio telescopes in New Mexico, an array of radio telescopes. Just to give you guys a quick heads up, this is not a photoshopped image. This is just a long exposure photograph of the radio telescopes with the Milky Way. The next generation of radio telescopes, which are currently being built, are going to be so sensitive that they could detect Earth-like radio waves, Earth-like radio emissions, up to something like 100 light years away. Now, within 100 light years of Earth, there's something like 10,000 other stars. And about 10% of them could potentially be habitable. So with the radio telescopes that are being built right now, we could potentially detect signs of technology on maybe 1,000 different habitable worlds within 100 light years of our own solar system. Isn't that extraordinary? Now, we have no idea what fraction of those 1,000 planets is going to develop life and what fraction could develop intelligent life that we could communicate with. But just maybe, if you've got 1,000 planets out there, you might just begin to seriously speculate that we might actually be able to detect signals. So that really is a kind of super exciting prospect. Now, just before we wrap things up for this afternoon, I would like to share with you guys just one more destination, just one more planet on this tour, okay? And I think you guys are really going to like this because I really have saved the best for last, okay? So this is a terrestrial planet, okay? We know there is water vapor in the atmosphere, okay? So it really kind of is a very exciting planet. I think you guys are going to like it. Let's take a look, okay? Of course, it's planet Earth, okay? And the point I'd like to make here is when you look out in space for signs of life, I think it really does give you a different perspective of life on Earth. And this is certainly something that you see from astronauts who have gone and studied space. But I think, gone and traveled to space themselves. But I think it's something that you can really get a sense of just by studying space and studying the search for life right here on Earth. One of the real landmark images, in all of astronomy, and it really kind of puts planet Earth in a bit of context, is this beautiful pale blue dot mission championed by Carl Sagan and taken by the Voyager 1 mission. How many of you guys have seen the pale blue dot? Isn't it just beautiful, right? So planet Earth, we're just right up there. That tiny little dot there, just a few pixels up there. Now, this was taken in 1990, okay? So if you were alive in 1990, you're in this photograph here, right? Think back to what you guys were doing in 1990. Were you guys on another cruise or something? You're in this photograph. It's a photograph of everyone. And it really does put our own planet in a bit of this cosmic perspective there. And, if you think maybe if there's some other civilization thinking, is there any life in this rather unremarkable solar system, their first view of Earth might not look too dissimilar to this. I'm not sure which month, but I'll have to ask you. If we look a little bit closer, even before the pale blue dot, there's this beautiful picture taken by Bill Anders on Apollo 8 of Earthrise here. How many of you guys seen this photo before? Yeah, it's just beautiful, isn't it? This was the first time that humans had seen Earth rising over another celestial body with their own eyes. We'd seen this kind of view from robotic spacecraft, but seeing it with their own eyes. And again, it really does put our own planet, our own beautiful planet, in a kind of bit of a different context here. You know, if you think we're searching so hard out in the cosmos for just the faintest hints of microbial life or a little bit of dimethyl sulfide, but we're living on this beautiful blue marble, which is just absolutely teeming with life. You know, everywhere you look, it's just full of beautiful life in these coral reefs. And, you know, we've been looking so hard for signs of liquid water. And, you know, we live on our own beautiful planet with all these beautiful rivers, and it's just absolutely teeming with life. And I think you can't help but appreciate life on Earth all that much more if you put it into a bit of that cosmic perspective there. Now, I'm not sure what you guys kind of take away from all of that, but I think it really is interesting to, if we think about a bit about that perspective, it kind of really does put our own planet into a little bit of context here. Now, we're just about to wrap things up for this afternoon. Just before we do, I'd just like to share with you guys just one last time, because, you know, I've always been fascinated by space and time, and I love talking about space and time with you guys. And I love the questions that I get with you guys afterwards. And I thought for quite a while, people ask a lot of questions about things that you wouldn't find in, you know, a popular science book or something like that. So I wrote this book, First Steps in Space-Time. It was published just this summer, my very first book. And the idea is to kind of go into a bit more depth about space and time than you might get, you know, if you're reading one of these fantastic popular science books, but hopefully to be more accessible than like a university textbook. So nobody writes a university textbook to be read kind of like a novel or something like that. The idea is this might be a little bit more kind of readable, so something you might be able to kind of take off the shelf and read through. So if you have been curious about some of the things we've been discussing all this time here, especially, you know, kind of space and time dilation, that kind of stuff, I really hope you guys might enjoy this, okay? Now, until recently, this was actually available on level 6, and thank you guys so much, everyone who's bought a copy. Honestly, it just means so much, everyone who has bought a copy. I've got to say, though, it has actually sold out, okay? There's not a single copy left in the show. Oh, thank you, guys. Guys, thank you so much, honestly, it really, guys, honestly, it's just beyond a dream come true to have sold all the copies. Guys, thank you so much to every single person who has bought a copy of the book. Honestly, it just means so much. It really genuinely does. If you would still like to read this while you're still on vacation, you still can get a you know, an e-book. You know, you can read on your Kindle or your iPad or even on your phone. You know, wherever you get e-books from. Or, you know, if you would like to you know, order your own copy, it's kind of available in bookstores and that kind of stuff. But guys, thank you so much. I really do appreciate everyone who has got a copy. It really means more than I can say. Now, this is actually our last lecture here. And I've gone a little bit over time. It's too exciting. I couldn't fit this all in. Usually we have a bit more time for questions at the end. But don't worry about it, because they very kindly arranged a Q&A session on Friday. Okay, so it's going to be at 11:30 on deck 6 on the Roxy. So we're going to have a whole hour. Please do come along. Any questions about life in space or the invisible universe, or, you know, you just want to book your next space vacation, please do come along. And, you know, and, you know, we're just going to have a free-form Q&A session. So I'm really looking forward to that. Now, I have checked the ship's program. Okay, I am aware that this does clash also on deck 6. At the same time, there's an eye makeup tutorial. Okay. So if you have already booked onto the eye makeup tutorial and you can't make it, please don't worry, okay? Do just drop me an email. We can arrange some other time if you want to chat, okay? So we really should kind of wrap things up here today. But guys, I just want to say it has been an absolute joy talking a little bit about space with all of you guys this time. I hope you have a fantastic time on the rest of your vacation here. Thank you so much for listening. Thank you.